One note I'll make without proof is those pictures work in space. Now in space you'd have to draw level surfaces as opposed to level curves. That's why I'm not going to do it. It's harder to draw. But this method works very well for a function with 3 inputs, which you can't graph in space. But it's, if you set so w equals f of x, y, z has 3 inputs, 1 output, 4 variables altogether. You can't graph that in space. But if you set w equal to a constant, you're looking at a level surface. And this method works very well for that. So let's suppose you have f of x, y, w equals f of x, y, z, and the constraint is not a curve anymore, but a surface. It's still going to turn out to be true that del f is equal to lambda del g. And we're going to use that to solve the next problem. So let's find the extrema of f of x, y, z equals x squared times y squared times z squared on x squared plus y squared plus z squared equals 1. Okay, what is this? What is this surface? It's an ellipsoid, but more specifically, it's the unit sphere, centered at 0, 0, 0, radius 1. So it's very important you understand what the restricted domain is. It's only points from that sphere that you're allowed to plug into F. Does that make sense? Okay. If you keep your head about you, you can find the absolute minimum with no work whatsoever. What's the smallest this function can ever get? 0. Right? Now, that kind of common sense will help you in otherwise difficult problems. So let's make a note of that. By the way, I don't think we want to write down all the critical values that this would be true for. So let's just kind of generalize. What has to be true about any one x, y, or z to create 0 for an output? One of them has to be 0. So that's a whole bunch of critical points, right? There's a whole bunch of points on the sphere where you could have, like, one of those equal to 0, right? So let's say it this way. If any of x, y, or z equals 0, then f, I'm just going to write that. I'm not going to try to write down f of anything. I'm just going to say then f equals 0. It's clear, right? So the absolute minimum of the function is 0. Ultimately, when we talk about absolute extrema, we're talking about the height value, right? And I'm not really that interested right now, at least, in the critical points that would produce that. We just know one of them has to be 0, and that's enough. Since f is greater than or equal to 0, is that clear since all the exponents are even on x, y, and z, and it's a product? Since f is greater than or equal to 0, f equals 0 is the absolute minimum. Is it the absolute minimum on the constraint? Pretty much anywhere, right? So you're never going to get something less than 0, right? But it's also on the constraint. Is the absolute minimum on the constraint and anywhere else, but I'm not going to write that down. On the constraint. So why am I doing this first? Why am I bothering with this? Well, remember how in the last problem we couldn't assume y was equal to 0, and we had to factor it out when we got y equals 0 and lambda equals 1? Here, we've exhausted the possibilities where any one of those variables is 0. So if we want to divide out variables, we can, because we know we're not interested in the case where one of them's 0. Does that make sense? I'll say that again when we get to it. Let's go ahead and, oh, by the way, you could think of g as x squared plus y squared plus z squared minus 1. Again, that's a good habit, equals 0. Although, again, it really wouldn't matter in this case because when you take partials, the constant goes away. Anyway, let's set it up just like we did in the last problem. Del f, what's del f going to be? So focus your eyes on this guy. Take the partial with respect to x. 2 x y squared z squared. I plus 2 x squared y z squared. J, right? Does everybody see what I did there? Partial derivative of f with respect to y. That goes in front of the j. And then in front of the k, 2x squared y squared is just z times k. So you do have 3 components, as somebody already mentioned. Because it's a space vector. When you have 3 inputs, the gradient's going to be a space vector. Okay, everybody good there? Let's do the same thing for del g, and then we'll multiply by lambda afterwards. So this is a little easier. What's the, hold on, I don't like the way that looks. That's supposed to be a z squared right there. Okay, what's del g? 2xi plus 2yj plus 2zk. And then multiply by lambda. And then what do? Corresponding coefficients equal. Set them all equal. Okay? So what do we get? We get 2xy squared z squared equals what? 2, not x, but 2 lambda x, right? Oh, and try and make your x look different from the lambda. Sometimes it's hard to do. And then what's the next one? 2x squared yz squared equals 2 lambda y. And then the next one, 2x squared y squared z equals 2 lambda z. Then there's another equation you can write down. What is it? Yep, the constraint equation. X squared plus y squared plus z squared equals 1. How many equations do we have all together in the box? 4 equations. How many unknowns do we have? 4? Well, x, y, and z make 3, and then lambda makes 4, right? So 4 equations, 4 unknowns. Hopefully we can solve, right? So it's pretty easy to state the method, isn't it? And even to set it up. But the devil is in the details of solving the system. It's in the algebra, really, right? All right, how can we make our lives easier? Well, we can do both, right? We can definitely divide out the 2's, but also since we know x is not 0, we're assuming x, and it's, you know, it's never a bad idea to state that. So I'll go back up here and state that. So let's assume, since we already know what happens when one of them is equal to 0, let's assume none of them are equal to 0. Let's assume all of them are non-zero. And then what we're doing is okay. You're not dividing by 0 or anything. So for this equation then, this first one, not only can we divide out the 2's, but we can divide out the x's, right? And the second equation, divide out the 2's and the y's. And the third equation, divide out the 2's and the z's. And then, okay, I think it's getting a little busy, so let's write out then what we have. Y squared times z squared equals lambda. And then what? X squared z squared equals lambda. Oh, I like that. Then from the third equation, x squared y squared equals lambda. So, yeah, and I'm going to, so they're all equal to lambda, right? The left-hand sides of these equations. I'm going to set them equal to the left-hand sides equal. Make sense? And then it's going to work out. We're going to have a nice symmetry. And it's really due to the nature of the function in the first place. We're going to have this nice symmetry where y squared z squared is equal to x squared z squared. Whoops. And that's equal to x squared times y squared, because they're all equal to lambda. Did I copy? Make sure I copied all those down, right? I think I did. We can go even further. In the first equation, what can we get rid of? So focus your eyes on the first equation. We can cancel out the z squareds, which gives me, beautiful, y squared equals x squared. But wait, there's more. I feel like I'm selling you a food processor. Okay, second equation, what can we cancel out? So x squared, but then the z squared is still left, right? So that canceling is unfortunate right there. The z squared in the purple cancel line, that's still there. So z squared equals y squared, but y squared equals x squared. So they're all equal. So y squared equals x squared equals z squared, that's nice. Because look at that bottom equation in the box. Those guys that we're adding are all the same, right? You can call them all x squared, 3x squareds added together, 3y, it doesn't matter. 3z squareds added together. Let's make it all 3x squared. So from this equation, we're going to change it to x squared plus x squared plus x squared equals 1. Right, so it works out real nice. 3x squared is equal to 1. You do have to be careful here, though. X squared then equals 1/3. Yeah, so I'm gonna go over here. Just point at where I'm going to. X is equal to, you got to be careful, plus or minus 1 over root 3. Everybody see that? Does matter. We've got to be really careful here or we're not going to get all our critical values. Okay, I'll write it down, but again, we're going to need to be careful. So then what would y equal? Yeah. What would z equal? Now, you've got to be careful when you use this plus or minus. Because here, is there any reason why we can't mix and match pluses and minuses together, the coordinates? Now, all we know is why all the squared values are equal, right? That's all we know. So there's no reason why you couldn't create all possible critical points with pluses and minuses, pluses or minuses in front of the various coordinates. How many would that be? If you've never had statistics, that's it. There's a way to see how many ways you can do something. If there's m ways to do one thing and n ways to do another thing, as long as they don't interfere with each other, there's m times n ways to do both things. Here, there's 2 possible x coordinates, plus or minus 1 over root 3, 2 possible y coordinates, plus or minus 1 over root 3, 2 possible z coordinates, plus or minus 1 over root 3. 2 times 2 times 2 is 8. There's 8 critical points here. It's not going to matter a bit, though, is it? Because when you plug it back into the function, you square out all the negatives. You're going to get the same value for each critical point. I feel like we should mention it, though, in case it does matter, in case there's not everything's being squared in your function and you come up against something like this. So here's how we could list them all. So your critical points, so CPs for critical points, if you want to use a plus or minus, I think you'd have to only use it in one of the coordinates, right? And then, so how many can you get from plus or minus 1 over root 3? How many different combinations of plus or minus 1 over root 3 for y and plus or minus 1 over root 3 for z can you get? 4. So we've cut down writing 8 points to 4 points, essentially. So, okay, so we could have, for y, we could have, let's go all positive, y and z, both positive, right? So that's really 2 different points right there. Plus, with the plus x coordinate and the minus x coordinate. And then let's find an organized way to do this. Plus or minus 1 over root 3. Let's make the second coordinate negative. So negative 1 over root 3, and then positive 1 over root 3 for the third coordinate. Okay, and then what could we do? Okay, so are we going to keep the second coordinate negative? Doesn't really matter. We'll come up with the one we missed later on, right? So that, and then the one we missed would be where everything's, the second two are negative, right? So plus or minus 1 over root 3, negative 1 over root 3, and negative 1 over root 3. Did you realize that there's 8 critical points here? I shortened it to 4 using plus or minus on the first coordinate. Okay, what are you going to get? Now here I will kind of be a little bit liberal with the notation. F of any CP, it's going to be the same. You guys see why? I got to remind you what the function is. X squared times y squared times z squared. You're squaring out all the negatives, and the absolute value of the coordinates it's all the same, absolute value-wise, right? So what are you going to get? You square any one of these, you get 1/3, don't you? 1/3 times 1/3 times 1/3 is 1/27. Notice I didn't make a table in this one. This is the absolute max, 1/27, given by all of those critical points. And then, of course, the absolute min, f equals 0, is the absolute minimum. And this is on the constraint, right? That's the assumption. Okay? So these are your two answers.